Here is Mohamed Zahran. Mohamed Zahran is currently a professor with the computer science department at New York University. His research interest spans several aspects of computer architecture, such as architecture of heterogeneous systems and hardware-software interaction. Zahran is a senior member of IEEE, senior member of ACM, and the Sigma Xi Scientific Honor Society. He received his PhD in electrical and computer engineering from the University of Maryland at College Park in 2003. Thank you, Zahran.
Thank you guys for coming. And I'd like to thank Daniel for his great talk, after which I think I don't have anything to say. So I'll just take questions. All right. What we will be presenting today is a little bit of a crazy idea, but it's, it goes in line with many of the things that Daniel said. It has been done by my student, Chris. So if you see any caveats in the crazy idea that we are presenting here, it's Chris' fault. If you see anything that is good, it's mine. No, just kidding. All right. We call our paper Beyond Profiling. Profiling has been used a lot everywhere. It all starts with a program. You execute it in some hardware. You get an output if you are lucky. But with the output, we gather all kinds of gold mine profile data. This profile data has been used, as we saw in Daniel's talk, in many different ways. One of them is actually we are using this profile data to enhance our hardware, to reconfigure our hardware if we have anything that needs to be reconfigured. And here, when I say reconfigured, I don't really mean FPGAs. I mean, a branch predictor is kind of reconfiguration, the cache replacement policy, and all of these. Or we can use that in compilers, for example, in feedback-directed optimization, mini code optimization, and all of that stuff. The problem is, or not the problem, but the whole idea is we are talking about the same program and the same hardware. And with many of the online techniques that we have and that we have seen at Daniel's talk, we start the execution of a program. At the beginning, you are doing no predictions for a while until you gather some patterns. Once you gather these patterns, you start to build an idea how things are going, and then you start making prediction. You start adding more patterns and adjusting your prediction, and you keep doing this online until the end of the execution. Now, if you look at this picture, we can put it as if it is like training and inference, which is used a lot in the machine learning. I've been actually using the word, seeing the word machine learning even in my dreams, actually. There's a PhD of my wife in artificial intelligence. 90% of the professors in my department are doing machine learning. So basically, in order to be politically correct, both at home and at work, I have to do machine learning. So basically what we see here in this slide can be applied to many things, or is applied actually to many things, for branch prediction, data value prediction, cache replacement, cache power management, all of the things you can think of. Now, our hypothesis is related to a key word in this slide, which are patterns. We are all dealing with patterns. Okay, so what is interesting about this? In a pattern, you see patterns of the branches, taken, not taken, taken, all of that stuff. You see patterns in the cache access. Okay, so you can design some cache replacement and all of that stuff. Okay, how can we make use of something like this? Our hypothesis is the interaction of any software with any structure of hardware is based on patterns. Okay, what does this mean also? It means you can disregard the program and just see a flow of patterns. If you can gather these patterns and learn them, then you can actually do good predictions for any program. So it's all about patterns. If we can learn the pattern, you can get useful info for any program and for any program. which means basically this is what we meant by beyond profiling. You can take the profile data of one program to make a different program work more efficiently. Okay, that was crazy. That was Chris master's thesis. And we still have way to go, but we tried to have some proof of concept or something like this. Generically, you can think of it as you are executing a program. During the execution, you can cut the execution type into windows, and in the window, you can see what is the best hardware configuration for the patterns you are seeing. And then you gather this information, and during the execution, you see, okay, that new program that we haven't seen before, is it generating the same pattern? If it generates the same pattern, then we have the best configurations that we have seen in the training part. Okay. It looks like it is a very nice, very straightforward problem to be done by machine learning. But the problem is, well, not the problem, we tried machine learning here and we will show the results. The problem is something like deep neural network works very well in many domains, but we don't know why. This is a problem. And this is why we have deep networks. If we can open this black box and see how these things works, we can get the same prediction, but with much less hardware or resources needed. How do we do that? I have no clue. This is still an open question. I know at least of 2 research groups who are working on this to try to open this black box. But what we are trying to see here is, okay, whether we can find the best configuration for some programs and then use this information for a totally different program. Yes, and the proof of concept is here. We wrote 4 toy programs, and it is toy, we have made them toy programs willingly to show that with very small toys, we can make much larger programs work much better. So with just very small programs, with very small input sets, we made the benchmarks parsec do much better. But we need to pick an application to prove this. When we say much better, we didn't say much better in what. So as our proof of concept here, we picked the cache power management, turning off some slots from the last level cache to save power while keeping the performance intact as much as we can. Okay, so we decided to try this. I didn't choose this colors, it's Chris, just in case you don't have it. So basically, these are some of the parsec programs. The very first bar in every program, this is a full cache. Okay, that is, we didn't turn off anything. And then we calculated, we used a neural network for that. We use Bloom filters because you know that a Bloom filter is really a structure that can map some signature to say whether it is member of that group or not. So the groups here are the configurations. The inputs are the signatures that comes from the program for every phase during execution. So if we have, let's say, 4 configurations, we have 4 Bloom filters. We get the signature, it will tell us, okay, it goes to that configuration. And also, for the sake of comparison, we use the EWSS, the extended working set scheme by James Ness long time back, and few papers have been using it a lot. It actually checks the Hamming distance between addressees of the instruction cache to detect the phase change in the program behavior, and when there is a change in the phase of the program behavior, it takes a window of instruction to try different configuration and picks the best one for a long time, and then until it takes a phase change again, test some configuration, pick the one. So as a sake of comparison, we use also EWSS. And basically, the y-axis is the average last level cache size that was working, which means the shorter the bar, the more we turned off from the cache. Okay, so if you look at the y-axis also, we have picked a very small size for the last level cache, which is 1 meg, to make it very sensitive to any perturbation. We want to see, actually, when we turn off something, how much performance loss we can get. In our neural network and Bloom filter, we actually we were actually able to turn off many, on average, a lot of caches. Now, what do you think the overall performance can be with something like this? This is the miss rate of the caches, overall of the last level cache, after we turn off the stuff, which actually we didn't lose much of the cache. I mean, higher is worse in that case. We didn't lose that much of the performance here. And this is basically the overall performance, which we have negligible performance loss. And we, in some applications, in some programs, we turn off as much as 60% of the cache while keeping the performance. We're using 4 toy programs to make a parsec doing much better in cache power management. It all depends on the hypothesis. If we can get the patterns, you can mine the profiling data of one program to make many different programs as efficient as possible. We are currently trying this with different other applications, cache replacement, branch prediction, and even in some system software, the operating system scheduling, because at the end it's all a question of patterns. If you have single-thread program, multi-thread programs, multi-programming environments, at the end what you see, what the hardware architecture or structure sees is a bunch of patterns. If you can learn how to deal with this bunch of patterns, then basically you can get useful information from any program to enhance any other program. That was our proof of concept. I mean, we still have a long way to go with something like this. And actually, to give you an idea, this is our roadmap. This picture is not Chris. I just stole it from the internet yesterday when I was at this cafe downstairs. Basically, we need way more sensitivity analysis. We didn't have the chance yet to study the different signatures, because it all depends on the signature that you map. It all depends on how many configurations you want. So we need more sensitivity, more test cases. Test cases here, I don't mean more programs in the benchmark. I mean, we will try it in use cases, cache replacement, branch prediction. Actually, can we go back to static branch prediction using this technique? So in this case, the branch predictor can be quite good, but without using online data until the program ends the execution. Will this help us deal with Spectre, for example? Because the Spectre is actually depends on the dynamic branch prediction. Can we generate the patterns that we are talking about without even using toy programs? Can we have the design space being explored all the way, generating all kinds of patterns, make the machine, because this is done offline, so we can do it as long as we can, gather the patterns, see what is good, and then apply it right away. Can we combine online and offline, which is the continuous learning and relearning techniques as you run? So this means the machine will be better at executing any program. As you keep executing more and more programs, you are generating more patterns, you can update what you have learned, and so on. So we are exploring all of this. So our conclusion now, based on this, is the hardware configuration or reconfiguration depends on patterns, just patterns. It doesn't matter which program is generating this pattern. We can use actually these extra patterns from any profile data. Extract, actually, I forgot the word. So this is Chris. The more profile data we have, the more patterns we will learn. That was our proof of concept, and I'll be ready to take questions. If you think it's too crazy, feel free to say so. Before we submit it to the next HPCA.
I would like to ask a question about your results. So on the result of page of this week, that week, yeah. I don't know whether I fully understand. It seems like the difference between different benchmark varies a lot. but the difference between different algorithms doesn't vary a lot. Does it mean that your algorithm is still not very good at the generalization? It means that it only works very well on some benchmark that have very regular memory access pattern, but not work well as good as we expect on some very difficult benchmarks. Thank you.
Okay. Well, the thing is, yeah, with some benchmarks you will find different, but this is not, we didn't make any changes to the cache replacement policy, for example, or something. We are just turning off some slots from the cache, making some sets getting a little bit smaller, okay, just to save power. So basically what happens is that our algorithm was able to pick, based on the pattern, some sets that are not very heavily used, and we turn off them. So basically, this means that the cache replacement didn't find any problems in this. So basically, all the programs are the same. And actually, this is a subset of parsec, but actually we have the whole parsec set, which is very similar.
Hi, I'm Joe Lee from Seoul National University. Thanks for the great talk. I just wonder whether this pattern is kind of microarchitecture dependent. So if you learn some pattern from a specific microarchitecture, can it be applied to the other microarchitectures or system designs as well?
No, actually, the pattern here, I mean, based on this picture, it's not generic like any software within hardware. I mean, that piece of software with the branch predictors, there are a set of patterns that are useful. That piece of software with the cache replacement has a different set of patterns that are useful. So for every piece of hardware, there are some patterns that are useful. We can extract these patterns from any profile data. If the question is whether this pattern will be useful for a different program, if you think about like a branch prediction, if you have taken, not taken, and then taken, not taken, this will work for anything. It is just a pattern. You know that if you see 1, 2, 3, 4, and then you see 1, 2, 3, the next will be 4, right? So some other programs may have a different patterns. We are learning this too. So basically, you keep adding to your arsenal of patterns.
All right, let's thank the speaker again.